Testing, 1, 2. Okay, this lecture is Limits Part 2, and today we're going to talk about some of the geometrical origins of limits, and then we're going to move up to a more or less rigorous definition, the epsilon delta definition of the limits. But I want to first motivate it by going a little bit out of order. I want to look at several Java applets that redo Archimedes' construction or his calculation of pi by means of inscribed and circumscribed polygons. That will lead into the idea of a limit of a sequence, and then we'll talk a little bit about the role of recursion. I'll explain what the word recursion has to do with limit in just a minute. That will lead naturally into topics that are seemingly pretty diverse of fractals, chaos, and dynamical systems. We'll give you a quick overview of that. Then I want to just redefine more or less how limits have to do with functions, continuity, integration, etc. And then there's a couple of more or less pathological functions. The Weierstrass function, which is continuous everywhere but differentiable nowhere, and Cantor's function, which is really extreme. It's a continuous differentiable function which is increasing, non-constant, and the derivative is 0 almost everywhere. So that's kind of an unusual function. And then an applet that I actually wrote for a calculus course on Riemann integration. And I want to end it up with just a brief discussion on why limits are difficult to teach and why they're hard for students to understand. Okay, so the first part I'd like to do is just click on this applet demo. Hopefully these applets will run without too much trouble. If they take too long to load, I'll pause. Looks good. It's loading all the classes. Okay, let me pause it for a second because I've had problems. Okay, this is an applet that allows you to visualize an inscribed polygon of whatever. Now that's unusual. Let's try reloading the page again. Okay, so here's an inscribed triangle. Now you can calculate the area of this triangle because these are 60-degree angles, 60, 60, 60, and if you put a point right at the center, you can calculate the length of the diagonal and calculate the area. You can add, of course, one. Okay, this is not good. So, okay, here is inscribing successively larger and larger sided polygons, and you can see clearly as the number of sides goes, the inscribed polygon approaches the circle and the area approaches it. Now, Archimedes actually calculated the area of a 96-sided regular polygon, which looks like this, which is pretty close to the circle. The next applet will pop up an applet that actually reproduces Archimedes' construction. And the graphics are messed up a little bit. Okay, we've got this all lined up. So in this particular applet, you have to click on this page to start the applet, and it gives you a control panel. And let me just get rid of all of these. So what you can do is you can draw the inner one. This is 4 vertices inside, 4 vertices outside. If I increase this to 5, 6, 5, 6, now we have an inscribed hexagon where the circle is inside here. Now if you wanted to do it on a 10-sided, 10, on the inside, 10 on the outside. And you can see gradually what's happening is the yellow shaded area is the difference between the two. So obviously the area of the circle is in between the green and the yellow region. And this gives you a bound between 2.93892626 as a lower bound and 3.24. Now if you were to do it like Archimedes for 96, and do the outside for 96, you can see that the inscribed 96 gon is very, very close to the circle. And how close is that you've got, okay, this actually should be, I guess it didn't update it when I drew, so I'll have to tweak this just a little bit. Okay, so you have an estimate that pi is between 3.14103 and 3.14271. So this was Archimedes' best approximation to the area of a unit circle, which was pi, by means of inscribed polygons. Okay, we can see how Archimedes would approach this. I think I can actually draw a circle much better than I can by doing this. And actually, let's put it in between here and here. So we know how to bisect triangles, so we can actually form a square by just connecting these. And we know this is equal to the square root of 2, because this is r equals 1 here, r equals 1 since it's a unit circle. And the area is pi r squared, which is just pi in this case. So if we get an area of the inscribed n-gon, we can get a numerical approximation to pi. So we know since this is 1, this is 1, this is equal to the square root of 2. And so you now have, you can calculate the distance between this and the perpendicular to this line. So you can calculate this as 1, and this is a right triangle, so this is 1 square root of 2 over 2, and then this is a certain length L. And you can calculate the area of this triangle as 1/2 this base times this height. So you can calculate the area of this triangle. Now, if you successively bisect this, suppose you now bisect this angle here, and now you want to calculate the area of this, which is 1, 2, 3, 4. This is 1/16 of the angle. So this is part of a 16 gon. And then you can bisect this successively and calculate finally this, which is a 32, 64. And actually if you started with thirds, which you can actually trisect the right angle, right, because you know a 30-degree angle, and you know how to calculate the length of a 30, 60, 90 triangle. So it's not true that you cannot trisect any angle, it's that you cannot trisect an arbitrary angle. You can only trisect special angles like 90. So I should probably mention that, is that 90 degrees, if you trisect it, it's 30 degrees. And we know in a 30, 60, 90 triangle, if this is 30, 60, 90, what the area of such a triangle is, right? Because this will be 1/2 and square root of 3 over 2. Yeah, square root of 3 over 2. Okay, so we do know this property. And if you take 30 degrees and bisect it 4 times in succession, then you'll have a 96-sided polygon, and you can calculate the area of that triangle. So Archimedes actually had a very good approximation to pi as a 96-sided regular polygon. So he could calculate pi to quite a bit of accuracy. Okay, so let's go back on this one. So what this brings us up to is the idea, if you now have a sequence of numbers that come closer and closer to pi. So the question is, if you have a sequence of numbers, and that's the important thing, you have a number, say, P1 is approximately 3, say, 0.0. And suppose P2 was 3.1, and P3 was 3.14, P4 was 3.141. So obviously these are the successive digits of pi, etc. Of course, this etc. is exactly what we mean by the limit, so we can't just hide it in terminology this way. So we want to know, what is the limit? And first of all, what do we mean by a limit? And the second, how do we compute the limit or verify that the limit? So let's suppose we have a number pi, just pick a number, is the limit. Now we know it's the limit because of the way we're constructing a sequence, but what does the limit mean? Well, one intuitive idea of the limit is that this sequence of numbers, P1, P2, P3, etc., if we look at the difference, P1 minus pi, P2 minus pi, etc., as we go down and then the arbitrary sequence element, these numbers should get what? Become smaller and smaller, right? So these numbers should become smaller and smaller. Eventually, they become arbitrarily small. So what you have is, if this is the number pi, this sequence of numbers actually comes up from below, P1, then to P2, P3, etc. We could also have a sequence of numbers that come down from the top. And the idea is if we bound this number by 2 known sets of numbers so that this number pi is trapped between these 2 numbers, and if the distance between this delta or epsilon, whatever you want to call it, actually let's call it epsilon for later purposes, this number epsilon gets smaller and smaller, and it actually goes to 0. So this is sort of what geometrically we mean by a limit, right? We want a sequence of numbers that approach a limit because the difference between these numbers and the ultimate limit goes to 0. Now, it's important, before we actually write down what the limit is, you can verify a limit by a formula, by the epsilon delta formula, but you're not going to actually compute it necessarily by that. So let's go and ask what we mean by the classic epsilon delta definition of a limit. So this is something everyone's seen in calculus, at least if you are a math major. If you're not a math major, engineering kind of typically skips this version of calculus. So what do we say when we say that f of x approaches a limit L as x approaches A? What does that mean? Well, graphically, we know what it means. If you can graph this function, this is not the world's best graphing program, but suppose we have a number here, A, and the function value is some number L here. what we're doing is, as x approaches, as we take a series of x's and look at the series of y's, as these values approach a from either side, we approach this number along the graph. Now, you can actually calculate, of course, limits of functions that don't have graphs or are not continuous. I'll show you a case in just a second where that's the case. But it's clear what you want to do here. So what you want to show is that if the function approaches this point, that as you get closer and closer to this value, you're trapped inside some box here, if you will. And the idea is if you can give the vertical dimensions of this box as, say, 2 epsilon, I'll explain the 2 epsilon in just a minute, as long as you stay inside a box of width 2 delta, if you can ensure that your function values stay within a box of 2 epsilon, and as you shrink delta and epsilon, you're going to be eventually achieve a box with this only this single point. Okay, that's the idea. So, and this was actually the triumph of Cauchy and Weierstrass, that they were able to articulate this concept as something that was mathematically treatable, verifiable, algebraic, involving inequalities and distances. Okay, so this approaches L as x approaches A if the following is true. If given any epsilon positive, that means any vertical, we can find a horizontal distance such that, and we all know what comes next, if x minus a is less than delta, and that means x is delta to the left, delta to the right, or inside a distance 2 delta, then f of x minus L is less than epsilon. And of course, we don't ever let it equal A, so we have to put that in. So this is the classic epsilon delta definition of a limit. If given any vertical tolerance, epsilon, I can ensure that the function values always lie vertically between these bounds by restricting the horizontal limits of this box. Then, as you let the epsilon go to 0, the delta shrinks, and if it contains a single point at the end, that has to be the limit. Now, it is not true that the function has to be graphable or even continuous to have a limit. So, for example, here's an example of a function which is not continuous, but has, except at 0, but has a limit at 0. It has a limit. Well, obviously, if it has continuous, it has a limit. So just look at the function f of x is equal to 0 if x is irrational, which is most everywhere, and it's equal to x if x is rational. So what is the graph of this? Can you graph this? Well, I'm not very good at graphing the rational numbers. There's a lot of them. But you can see what's happening is the following. For all of the rational numbers, I've got this graph. Now it has holes in it because at all the irrational numbers it's 0. So clearly, the function cannot have any limit other than 0. Now at 0, it does have a limit because both of these cross there. So the limit of f of x as x approaches 0 is what? It's got to be 0, right? But anywhere else, does the limit as f of x as x goes to 1 exist? So here's x equals 1. Now, 1 is, in fact, rational, so the function takes on a value here. But what's the problem with saying that f equals 1 is a limit? can I ensure, if I pick an epsilon up here, that I can stay within that vertical height by sufficiently restricting my x's to be in the neighborhood of x equals 1? Well, look at the picture. Is it true that for every x inside this horizontal window that my f of x lies within this vertical window? No, because there's always an irrational number in any interval, so there's always values of 0 and non-zero, and as you shrink epsilon, it's too bad, you can't get it. So this has no limits other than at a single point. So this is an example where it's not continuous anywhere, but nevertheless has a limit at 0. Okay. Now we're jumping the boat because I've actually used continuity without telling you what it is. So forgive me for that. Now, that's the classic epsilon delta, and what this does, let's go back, is it gives you a very precise way of verifying whether a number L is in fact a limit of this function, because it has to satisfy this statement. Now this is a rather complicated logical statement, and you've probably actually seen a very concise mathematical, if we use the notation this as for every, and this backward z for there exists, and this as such that, and this meaning if then. Mathematicians often write this limit definition as for every epsilon positive, there exists a delta positive such that if x minus a is less than delta, then f of x minus L is less than epsilon. Okay, so if you want, this is equivalent to that, but it's been, all the English has been stripped out of it. So mathematicians like to do this, strip away the English and leave only the mathematics. But the real power is that you can reduce it to logic, if-then statements, inequalities, things that you can check. And so I would like to point out at this point is that from this limit definition of it, you can verify a limit, but you can't construct. In other words, if I gave you a function that was very, very complicated, like this Weierstrass function I'll show you in a little while, and I ask you, okay, what is the limit? Or if I give you a Cantor function and say, what's the limit? The problem is you know it's continuous. You can show that it's continuous mathematically, but it's very difficult to actually calculate the value at a particular point. Okay, so everyone sees that this is not a constructive definition. This just says if you can satisfy this definition, then the numbers L and A that you pick have this relationship, then the limit of f as x approaches A is that limit L. It doesn't tell you, given A, what is L. Okay? So in other words, if I say limit of f of x as x approaches A equals some number, you can't find this number by applying the definition unless you have some other machinery. Okay. So that's an important point, and that also leads to some confusion on limits. Okay. Here is an example of a kind of an exotic set, and now this comes under the title of recursion, and I'll explain what recursion is after I go through the Cantor set. Now the Cantor set, as you may know, is a set that was constructed that essentially was almost empty, but nevertheless had some very interesting properties. So what the Cantor set was is you started off with a line segment, and you remove the middle third. Then you take these line segments to the left, and that's 2/3, and you remove the middle third. So this is now 1, 2, 3, 4/9, and you remove the middle third. So there's 1, 2, 3, 4, 5, 6, 7, 8 18ths, so or 27ths, and you keep removing it. And clearly, if you keep removing these, what's going to be the length of the line segments that remain? Well, it's going to be 0, because you'll end up subtracting off a set of measure 1, of length 1, from a unit interval, so what's left has to be a set of measure 0, meaning that it contains no intervals. So what's left is called Cantor's dust. So you might, as they say, ask, is there anything left, because when you sum this series, it's equal to 1, and if you remove a sum of lengths that add up to 1, you'd say, well, what is there left? Well, obviously you could leave a point. You could take 2 half-open intervals.
If your measure is 0, then that means you have a finite number of elements left?
No.
But a finite set has a measure of 0, right?
A finite set of points has measure 0, but this is an infinite process, and it's not clear whether you leave a set of points or something more complex. You cannot leave an interval, because if you have an interval, you're removing pieces of that interval. So no interval can survive. So somehow the only thing that you left is some very strange exotic set of points. Now the set of points does have measure 0, and there's actually a Cantor went ahead and defined a function using this process called the Cantor function, which is really an interesting function. We'll get to it at the end of the lecture. Okay, so this is the process here, and there's more of a visual. Now, one of the ways the Cantor function is defined, okay, the Cantor process, okay, this is, again, the process due to Cantor. You take away this function, the middle thirds, or you can actually divide it in the thirds, and you could say, okay, a function 0 here, 1 here, and a half here. Now take this function here and divide it into middle thirds. Now this is a half here, so divide this to be 0, quarter, half, and then keep on going. So what's going to happen if you keep on subdividing this is the function's always going to be increasing on any interval, right? From one interval to the next, it's increasing. So the function's never decreasing. It's always non-decreasing. The function is always composed of a series of line segments, all of which have slope 0, except at the endpoints. So then if you look at the limit of this construction, you're going to get a continuous function that's always increasing, that's formed of a limit of functions, all of whom have vanishing derivative everywhere. And you can show that the function is in fact continuous and differentiable. So you end up getting this following very strange function, the Cantor function, which is continuous, has a derivative, it's non-decreasing, it's non-constant, but the derivative is 0 almost everywhere.
Wow.
So that's kind of an interesting little guy there. Okay. Now, this idea of recursion is exactly the following. When you apply a operation to itself. Now, we've all seen recursion. So, suppose you have a calculator, right? Here's my little calculator with buttons. And suppose you just keep on hitting a button. You calculate, say, sine of 1. And then you take the sine of the sine of 1. And then you take the sine of that, and then you take the sine of that. You just keep taking values, etc. Does this have a limit? So in other words, if you have a function, f of x, and if you define the next value as the function applied to the previous value, which is, of course, f of x minus 1 etc. So you end up with a sequence of values. x0, f of x0 is x1, f of x1 is f of x0, that's x2. Does this actually have a limit? Does the limit as n goes to infinity, not xn, does the limit as n goes to infinity of xn approach any number? Well, this is a rather strong requirement, because when does a sequence of points as n goes to infinity approach a value? Well, the difference between the limit, say if it were existing, say alpha, xn minus alpha would have to go to 0. Okay? And you would show that by your epsilon delta proof. Now, you would possibly guess what the alpha is by looking at a table of values, say. But what can happen is the following. A function doesn't necessarily have to have a limit. Okay, so when does this have a limit, this process? Well, it clearly, if xn approaches alpha, where does xn plus 1 approach? If x1, x2, x3, x4, xn go to alpha, then x1, x2, x3, x4, xn plus 1 has to go to alpha also. So if all your points go to alpha, then all your points go to alpha, because the whole set of xn's is the same as the whole set of xn plus 1. Now, apply this to both sides of the equation. If this goes to alpha, and if f is continuous, which we'll assume it is, what is a continuous function of f of x as xn goes to alpha? What does that approach? Two guesses. F of alpha, right? Because that's the definition of a continuous function, right? The limit of f of xn, you pull the limit inside if f is continuous. F of the limit is the limit of the f. Now, if f of alpha is equal to alpha, that's a necessary requirement. Now, it's not sufficient because f might not be continuous there. But this is necessary if that has a limit. Now, does anybody know the name of this relationship, what this is called? It's called a fixed point. Now, it's pretty clear to see why it's called a fixed point, because when you apply f to it, f of alpha is alpha, f of alpha is f of alpha, which is alpha, etc. So no matter how many times you apply f of alpha, this is alpha, f of alpha is alpha, no matter how many times you apply it, it doesn't change. Okay? So this is a fixed point of the mapping. Now you may ask, when does a function have a fixed point? And is that fixed point the limit of this sequence? And you can actually show there's some conditions that certainly f should be continuous there, and if f is differentiable, then f should not have a derivative which is positive or bigger than 1. Okay, so let's see that. Suppose we have a function now we're going to make, this is f of x equals x. So I'm going to draw my function here. And this is a point where, what's true? This is my alpha, and this is y equals x, and this is f of x. Where f of x crosses y equals x, what's true? The y value is alpha, the x value is alpha, so this is what? Possible fixed point candidate. So where it crosses this line, I obviously have f of alpha equals alpha. Now let's see what happens here. If I start off with an x sub n here, what's the value of f of xn? How do I calculate that? Well, I draw a vertical line. Hard to draw a vertical line. And this is the height anyway, is my xn plus 1, right? Now where is that value? Well, if I reflect it sideways here, this is my xn plus 1. Right? Now if I take the next value, xn plus 1, the y height is here, and I keep moving in like this. So what's happening to my sequence of points? If your function, that wasn't a good, I should have drawn the line. Okay, if your function crosses at less than a 45-degree angle, what happens is you get this stair-step approach into, and the same like this. So it's clear that the sequence of points is going to converge to alpha. So if your f is continuous at alpha, and if f of alpha is alpha, and f prime is less than 1 in magnitude at alpha, then xn plus 1 equals fxn is a fixed point. It converges. Now, what happens if the other case is true, if it's steeper than 1? And so let's cross it like this. Okay? So here's my f of x, and here's y equals x. And here's my axis. What happens here? Well, here is my point. Suppose this is my point here. How do I calculate it? Well, I go up here until I calculate my xn plus 1, and now I'm over here. Whoops, I've moved away. So here's my xn plus 1. So then, if here's my point up here, I go up here, and I calculate, whoops, I move even further, and I keep on going, and I keep, what happens to the series of points? You move up here, reflect to the diagonal, you're further away, and you're further away, so this would actually diverge. So if your f prime is positive, bigger than 1 everywhere, then you're actually going to have a divergent sequence. Okay, but these are not the only two cases. You could have a case, which is now the really interesting case. I can't really draw this too well. But you could have a case where you would have like a parabola, where you could have this. You start off with a point, and then let's draw a line here. Let's try this. So you reflect the point here. So you go up here, you find the value, go over here, you go here, and now you're outside over here, and now you're down here, and then you're here, and you're here, and you're here. So you can spiral in like that. Now that's also one possibility, but you could possibly have a place where you just spiral around. What if you actually came down to a square, where this value reflected through the function gave you this value, but then reflected through the function gave you this value. In other words, suppose you had a case where you alternated between, say, plus and minus 1. Right? Suppose your sequence of values went minus 1, plus 1, minus 1, plus 1, minus 1, plus 1. Now, this sequence obviously does not converge, but you can look at two subsequences, two smaller sequences, minus 1 and 1, that do have fixed points. So this equation, xn plus 1 equals f of xn, may not converge. It can oscillate. It could oscillate with 1, 2, 3, etc. Now, what happens when, and normally your functions are going to be functions with a parameter. So if I have a parameter f of alpha, and I have xn plus 1, depending on what alpha is, I could have 1 fixed point, 2 fixed point, 3 fixed points. And what happens, and I'm jumping the gun just slightly, is this leads to a process called bifurcation. up to a certain very nice value, alpha 0, I have one fixed point. Then it splits off into two fixed points. Or not two fixed points, but two, it oscillates between two numbers that you can see here. And then this splits off into 4, and in a little while this will split off into 8, etc., and then on. This is sometimes associated with what's called period doubling or chaos. Because as you go along here, there may come to a point where it's just all over the map and you just can't tell what the function's doing anymore. So I'll show you some links to this and also some applets. Now, the point of this was that recursion, applying a function to itself successively, leads naturally to a question of what is the limit. And as we saw, a sufficient condition for a limit to exist is if the function is continuous, it has a fixed value there, and its derivative is less than 1. And you can actually prove that alpha is a limit. Okay, let's do some applications here. The fractals, the links to fractals, there's a ton of them here. I won't even go through any of them. I'll just let you explore those on your own. I've written some notes. This is a little PDF thing that you can print out. I did this for a 308 differential equations class, engineering, fourth semester engineering calculus. And I put some links in, a little explanation of chaos for them. So in order to discuss what chaos is and periodicity and determinism, etc., I had to define some terms, and I put some links in here and some. This is actually a very famous example of a chaotic system. The line attractor is a very interesting set of differential equations. So let's blow that up a little bit. Here's the set of differential equations. A takes on a certain value, 10, B is 28, and C is 8/3. This historically was a system of equations that George Lorentz used to study weather. And one day when he was making a very long run, his computer had some glitch somewhere in the middle of things, and he had some data of an intermediate point in this calculation. So he thought, oh well, the computer had some problem, and power went out or whatever. I'll just restart the computation using this data set in between and continue as if nothing happened. Well, what he did was he resubmitted at some later time the values and then integrated the system and observed completely different results. What happened was when he took the data set, he truncated the values when he printed it out so they weren't the internal full representation of the floating point numbers. When he truncated it down to the 8th decimal point, that small deviation caused the solution of the system to radically diverge after a couple hours or so. So he thought that was just really unusual because after all, isn't there a theorem that says if you have a system of equations, there's continuous dependence? If you change the data a little bit, won't you change the results a little bit? And the answer is yes, but the continuous dependence is not global, it's only local. In other words, for a long time you can get massive changes. Now I made a bunch of links for this class, the 308 class, and there's a whole lot of links on experimentation. This, for example, is an applet. Wait for it to come up. Now this is the logistic map, which is exactly, if you take this, you bounce over to here and you go like this. So there should be a, click the field. You can see what happens here. Is there a reset? I guess I have to. Okay, so you can see what's happening here is you have a series of points that converges to a single iteration. So if this is my point where this parabola crosses a straight line, obviously the slope is less than 1, barely. Alpha is the slope. And it converges to 0. Now as you cross it, eventually you have a single fixed point. It's obvious that the series converges. Let me push that up a little bit. It's obviously the series converges as you increase this parameter, the parabola. You start getting this cyclical spiraling behavior. Now you have some oscillation, but it settles down. But if the parameter is too large, what happens? You get points that oscillate, like this green value oscillates between 2 points. This blue oscillates at a different point. So this red one will spiral into this here, this blue one will spiral into here, and this green one will spiral out again. And then you can have even more chaos here. Now see, like down here, you can't even tell what's happening. This is an indication of chaos. When you have non-periodic, non-reproducible motion. And this is just a continuous value. So you can see where you go from nice single limit point. Now here's an example of what's called period doubling. Then more, and then more, and more, and then gradually you see how complicated it is down there. So this is an example of a lot of the applets for fractals here. This is a applet that looks at this, again, parameterization, repeated recursive application of the function, and then sees what it does in the limit. Okay. So here you can see that there's basically a single. If you look here, what happens? Well, if you look in here, okay, this is, let's look at, you can see how incredibly complex this is in here. It's a very rich environment. I guess I have to expand it like this here. So you can see all of these branchings here. Let's do this branching in here. It takes longer and longer as you go here. So you can see how rich it is. This says that these are the two, like, quasi-fixed points here, and then those two split off, and the two split off into 4, then 8, and then eventually, right at this point, there is basically an infinite amount of activity happening. Now this is going very slowly, so let's cancel it. Okay. So the idea here was that we have a recursive process that gives you a non-fixed point or a non-unique limit. Now there are links between chaos theory and fractals, which I've made sort of, I've linked to this outline. It's a very nice example. Now, we've just touched base on what we call a dynamical system. A dynamical system, for our purposes, is just a system of differential equations which you integrate forward in time. But naturally, and let me just point out, anytime you integrate a differential equation, you can get chaotic behavior. Okay? Because what is this equation? Suppose I'm integrating dy dx equals f of x, y. In fact, let's not put x. Let's just put f of y. So let's not assume it's an so-called autonomous system. Well, what's Euler's method say? Well, this says that yn plus 1 minus yn over some delta y, let's call it h, is f of y n. So if I solve for this, it's just yn plus h f of yn. A function of yn that depends on a parameter h. And this is exactly the setup we had for our chaos and our dynamical system. So for some values of this parameter h, you could get a single fixed point, a limit set, or you could get two fixed points or two periodic functions, periodic sequences, subsequences, or you could get, as h goes to a certain value, infinite number. So this leads to a recursive or relationship. Okay, this is also the other name by which this is known, and you'll see this in the literature. This is called an iterated function system. And there are some deep relationships between iterated functions, which is the same as recursive, iterated function systems, chaos, fractals, dynamical systems, compression, fractional dimension, etc. So the whole point of this is that they all involve limits, because we want to know what does this equation do as this n goes to infinity, and that involves a limit. Okay, so the final, just to summarize, and we'll finish this next lecture, or maybe I'll finish it tonight on the web, is that there are some very fundamental relationships between recursion, iteration, and dynamical systems. So I think at the next lecture I'll start off with these discussion points of why are limits so difficult for students to understand, and why are they difficult to give clear, precise definitions on how to teach them. In other words, why does it take so long to learn about limits, in spite of the fact that they're so important? I have got one more applet that I myself